I like this topic about snowball Earth because it brings in some of the historical geology that we don't really focus on much in this course because we're more focused on physical geology. But it's also a nice story about looking at bringing together different patterns of evidence to build up this reconstruction of what went on in the past. And does tie in obviously with the glacial topic, even though we haven't done the glacier slides yet. So basically the idea with snowball Earth is that there have been times when glaciers have come down not only just into New York and Wisconsin and so forth, but basically developed so much that they covered the whole planet. And so the whole planet was enshrouded with glacial ice sheets, and hence the idea, the name snowball Earth. The guy who first really proposed seriously the idea of glaciers making it down to the tropics, which is basically what we're talking about here. This is Sir Douglas Mawson, who was working in the early 20th century doing stratigraphy and other geological investigations in Australia. And I'm not going to go into his work in great depth, but basically he saw the kinds of evidence that we would expect to see. What are some of the things we've already seen in the field relating to glacial activity?
Striations on top of rocks.
Okay, so the striations that we saw at Sam's Point, that glacial chatter, the carving out of the U-shaped valleys, as we've talked about with the earlier Earth Science photo of the day things we just looked at. All of those are different evidence of glacial activity. And he was doing his geological investigations in southern Australia and saw basically marks in the landscape that were clearly produced by the action of glaciers moving across the landscape. Therefore, he basically made the argument that sometime in the past, and he's talking Permian era sediments for what he was looking at, making the argument that there were, at that time, glaciers in Australia. And glaciers in Australia would mean what? Yeah, we don't see glaciers in Australia during the most recent ice ages, right? He was working, however, pre-plate tectonics. So what would be another explanation for why we might see glacial deposits, glacial marks in the landscape in Australia without necessarily invoking the idea that glaciers had made it all the way down to the equator? If we're saying, well, maybe the glaciers didn't come down to Australia, what's the alternative? Maybe Australia went to the glaciers. Okay, so we know continents have been moving around, and we know Australia has been in very different locations in the past compared to where it is today. So how do we know that those glacial deposits weren't just produced in a time when Australia was at a much higher latitude? Therefore, we could explain that glacial activity without invoking the idea that glaciers had covered the whole surface of the Earth. Frankly, that we are already mentioned this somewhat in terms of some of the evidence that was marshaled together early to support this idea of continental drift in the pre-plate tectonics era. So, today we see glacial deposits not only in southern Australia, but southern Africa, India, and here in Central America. Distributions we would not expect to see from how we know glaciers work lately. But, the way we can explain that is that all those continents used to be down toward the South Pole, along with Antarctica, and the glaciers developed there, and then the continents moved to their current places, carrying with them the evidence of glaciation. So while Mawson was the first one to really propose this idea of snowball Earth or global glaciation, he was doing it on evidence that really didn't hold up. Since then, however, other people have proposed more convincing evidence for global glaciation. And so what I want to do is just go through what some of that evidence is and talk about how it holds together to produce this story. Okay. So basically, we're talking about more convincing evidence that there's been glacial activity at low latitudes. Basically, snowball Earth, global glaciation would imply glaciers down in the tropics. And so what would evidence of that look like? How would we, first of all, identify glacial activity, and then how would we verify that activity was actually laid down when those continental masses were in the tropics? So we have to talk a little bit about reconstructing paleolatitudes for these different areas. But in addition, people have brought together other evidence that we'll briefly look at. So carbon isotope and oxygen isotope studies have been brought into bear here as well. Ironically, the abandoned iron formations that we talked about with that graphic about the humorous look at geology in North America, they come back into play, as well as carbonate deposits and iridium deposits. And all of these, I want us to run through what these pieces of evidence are, and then how it all fits together into a story. Okay. So, how do you tell if a glacier's been in an area? We've talked out in the field, we've seen striations, chatter marks, and so forth. But there are other ways of inferring that glaciers have been in an area in the past. So here is something that we haven't seen in the field. This is an example of a drop stone. Looking at that, what does it look like? Pretend we were out in the field. Get your geology eye involved, and what do you see? What are the observations that you can see with this particular profile?
It kind of looks like the outside rock has conformed to the, what do you call it?
So, the outside rock, you're talking about this?
Like the layers, yeah.
Oh, the outside rock.
Yeah.
Okay. So we've got this, and then we have layers that seem to be going around. Okay, so how would we explain that?
Maybe further back in time, the layered rock was not lithified and was softer, and then a glacier came and passed over some till and punched that rock in there and they're lithified around it.
Somewhat. I mean, clearly, let's first talk about how are these layers forming? They're being laid down as sediments, right? And then, as Brandon just said, those sediments had to be cemented and lithified over time. Before they are lithified, they're malleable, right? And you can have soft sediment deformations taking place in various ways. So imagine that we had layers of sediment here on the bottom of some ocean or lake bottom. Why would these layers be depressed down in the area where this rock is at? It's called a drop stone. Basically, think about having nice layers of sediment on the bottom of some bathtub. You take a marble and you drop it down. It's going to depress and disturb those layers. And then if you leave it sit there and have more sediments come, what are the new sediments going to do? They're going to go over the top. And they're going to go over the top in this way, and eventually they're going to get smoothed out because the first layers that have come down are going to be mostly scoured off the rock. It's not until the layers build up that the rock gets embedded. It's all soft sediments at this point, and then if lithification takes place, you end up with this stratified layer of sediments with a big rock in the middle of it. Now, Brandon, you talked about a glacier coming along and punching the rock down into here. That's typically not what happens. Let's assume that these layers of sediment are being laid down in what kind of an environment have I indicated here? Okay, so we can get sediments laid down by wind, in various locations, but oftentimes we get sediments laid down in, lakes, oceans, and so forth. If a glacier comes along, where is it going to go in this system? The glacier is going to float on the surface of the water here, right? And that glacier is going to have ice. And what else is going to be in that ice of the glacier? Dirt, rocks, all the crap that is picked up when it has scoured the landscape that it covered before coming here. All fine and good. Now, climate warms up. What happens to the glacier? The ice melts away. The dirt and the rocks, they don't melt away. What do the rocks do? They boom. Okay, that's why we call these drop stones. So, there are some other ways that you can get rocks embedded in these deformed sediments, but a very characteristic way of getting these drop stones is this mechanism here, where the sediments are still soft, they're deformable. A glacial mass of ice comes and covers over the water. When it melts later, all of the debris that's in that glacier is going to drop, and heavy rock like that is going to hit the sediments. It's going to bury itself in the sediments and then get buried, and leading to that kind of configuration. So looking for drop stones is an excellent way to know if there had been basically bodies of water that had accumulated sediments in the past that at some time had been covered over by a sheet of ice that had scoured material off the landscape. Okay. Tillites. Actually, there should be another L there. Is another possible indication of glacial activity. So when we talk about glacial till, what are we talking about? It was in the readings and it was in the slides I haven't shown yet. As the glaciers scour across the landscape, what are they doing? They're picking up debris, dirt, rocks, and so forth, pushing that ahead of it like a bulldozer. What do you get? What kind of material do you get being pushed ahead of the glacier? Is it well sorted, finely sorted material like you would get from, no, it's a jumble of everything. And so that's what we're talking about with glacial till. That till itself can then become compacted, cemented, and lithified to form a sedimentary rock called tillite or diamictite. And so looking for these kinds of deposits it's a possible indicator for glacial activity. Varves are alternating layers of sediment that you see being laid down oftentimes in paraglacial lakes. So these, so basically annual layers of deposit of material coming off of the glaciers being accumulated in the lakes with different kinds of material coming off at different seasons, getting this banding kind of pattern. So we can also look for vars as an evidence for glacial activity. Striations, as we've talked about, we've already seen these in the field. So we can go around the globe and look for evidence of these types of evidence of glacial activity, and we can say we see that sometime in the past there were glaciers here. Because of this evidence, we then have to figure out where was this chunk of land, what latitude was this chunk of land at when the glaciers were active. If this chunk of land was up at 50 degrees north latitude, there's really nothing to explain. I mean, we're not surprised by having glacial activity up there. But if that chunk of land, when it was subject to the glaciers, was down at 10 degrees north latitude, then that's quite a bit different story. Well, we can use paleomagnetism to determine where the sedimentary and igneous material was when it was produced. And so this gives us a way of knowing that this piece of South America was either down by the South Pole at this time or up by the equator at a different time. So by combining the evidence of glacial activity in an area with some way of dating that glacial activity and using paleomagnetism in the rocks of that outcrop to know what latitude the piece of rock was at when it was being subjected to that glacial activity, we can say there was glacial activity and it was at 47 degrees south latitude, and it produced these scars on the landscape. Or this glacial activity, this piece of land was subject to glaciation when it was at 15 degrees north latitude in the tropics. So by combining the evidence for glacial activity with the paleomagnetic studies to know where on the globe that activity took place, we can build up a case for global glaciation or not, depending on what the data show. So here's kind of a summary. There's a lot of data in this area. I'm not going to go into a lot of it, but if you look at areas that exhibit glacial features that are dated to the recent epoch or the Miocene, we see a distribution of latitudes that looks like this. So, what does this tell us? Where, during the recent times when we had glaciation, where were the glaciers? Either the north, well, this is just 60 degrees to 90 degrees. It could be north or south. But basically, all of the recent episodes of glaciation have been at high latitudes. Either up toward the North Pole, coming down, or down by the South Pole, coming up around. Same thing if we go back to the Paleozoic. All of the evidence we have for glaciation is on landscapes that at the time were at high latitudes. However, if we go back a little further, there have been two time periods that people have been really focusing on in terms of this snowball Earth idea. The Neo-Proterozoic, that is the more recent upper reaches of the Proterozoic era. So this is pre-Cambrian, pre-Paleozoic times. So about 650 to 750 million years ago for the Neo-Proterozoic, and about 2.2 billion years ago for the Paleoproterozoic. There's evidence combining the paleomagnetic studies and the glacial studies that show glacial features showing up where? In the tropics. Okay. So this is fairly decent evidence that, at least during those two time periods, we had episodes where glaciers were down in the tropical regions. If we have glaciers in the tropics, are we also going to have glaciers in the mid-latitudes and high latitudes?
Probably.
Yeah, pretty much so. Okay? The only way you get glaciers of the tropics is if the whole globe is pretty much covered with glaciers. Okay, so that's one or two, lines of evidence that are combined to build up this story that, at least at a couple of times in the past, there were episodes where glaciers extended down to tropical latitudes. I think I'll just mention these isotope studies without going into them in any great detail. Two different isotope systems can be used to kind of figure out what's been going on, both with the paleoclimate and with biotic activity, or the activity of organisms in the past. We've got oxygen-16 and oxygen-18 isotopes. Which of those is going to be a heavier atom? Oxygen-18. Oxygen-16 atoms are going to have 8 protons, 8 neutrons. Going to have an atomic mass of 16, obviously. And oxygen-18, how many protons? No. Still has to have 8 protons if it's oxygen, which means how many neutrons? 10. Okay. So it's got an atomic weight of 18. Oxygen-16 evaporates from the sea more quickly than oxygen-18. I mean, think of water molecules that have oxygen-18 atoms in them. They're heavier. Think of them as more sluggish. It takes more thermal energy to get them to evaporate. So in the ocean, you're going to have oxygen-18 and oxygen-16. Mostly oxygen-16, but some oxygen-18. But preferentially, more oxygen-16 is going to evaporate at a higher rate than oxygen-18. So water in the atmosphere is going to be, if there is interchange back and forth between the ocean and the atmosphere, then the atmosphere is going to naturally be reduced in oxygen 18, and the oxygen 18 is also preferentially removed by precipitation. So the more that you're interchanging oxygen and water basically between the ocean and the atmosphere, the more the atmosphere is going to be reduced in oxygen 18 compared to the ocean. If there's something that will cut off some of that interchange so that there's a smaller amount of interchange going back and forth, gives more time for the oxygen 18 to become, to get into equilibrium, and that reduction in the oxygen 16 is going to be itself diminished. So this just gives us a way of determining in the past how rapidly water was fluxing back and forth between the ocean and the atmosphere. The more water is fluxing back and forth, the more you're going to get that fractionation taking place, and the more the atmosphere is going to be reduced in oxygen 16. The slower the flux, the more that the atmosphere is going to come into an equilibrium, and it's going to more closely reflect the oxygen isotope ratio in the ocean. Same thing with carbon-13 and carbon-12. Again, carbon-12 would be 6 protons, 6 neutrons. Carbon-13 has an extra neutron. It's heavier. When we're talking about photosynthesis, photosynthetic organisms are going to preferentially take up carbon-12. They're going to be reduced in carbon-13. So the more photosynthetic activity you have, the more that fractionation is going to take place. What we've seen in the past, in these times corresponding to snowball Earth kinds of activity, we see rapid changes in the ocean sediments in that carbon-13, carbon-12 proportion. So this has been taken as an indication that there was a significant die-off of marine algae. Therefore, less photosynthesis going on in the ocean. Therefore, less fractionation, maintaining that that bias against carbon-13. And so I'm probably not getting that across to you well, but just think that in those times when the carbon-13 level increases, relatively speaking, that represents times when there's less photosynthetic activity going on. So there's this time period here where photosynthesis was markedly reduced in the ocean. Corresponds to the times when we see these glaciers. We're talking about in the Paleoproterozoic, when we're talking about those tropical glaciers. Same thing in the Neoproterozoic, another time period where we have reduced photosynthetic activity in the ocean. Why would global glaciation result in less photosynthesis taking place in the ocean?
Because they're so enormous that they probably block this sun from reaching the depths.
Okay, so you got much of the ocean surface covered with kilometers of ice. That's clearly going to reduce photosynthetic activity, and people are arguing that these signals where we're seeing these changes in the carbon-13 ratio represent that decreased photosynthesis in response to the oceans being covered over by glaciers. There's other evidence with banded iron formations. Again, under what conditions do we get massive iron formations, banded iron formations forming in the ocean? We had to have had increases in the amount of soluble iron, and we can get that only when there's no oxygen in the ocean. And then what triggers the precipitation of the iron? If the iron is only soluble in the absence of oxygen, if iron is all of a sudden precipitating in the ocean, what does that mean? Now, if it's precipitating, that means the oxygen's come back. So if you look at the banded iron formations, we see most of them are dated to about 2 to 3 billion years ago. And these iron formations were presumably associated with the fact that the early Earth atmosphere had no oxygen, photosynthesis developed, atmospheric oxygen levels increased, and then iron precipitated out of the ocean. But if you look here at about 700 million years ago, which corresponds to that Neo-Proterozoic snowball Earth time period, we see another round of banded iron formation occurring. How could that have happened if oxygen in the atmosphere caused all the iron to precipitate out of the ocean, 2.5 billion years ago? If glaciers are covering over the ocean and photosynthesis is reduced, what's going to happen to the oxygen level in the ocean? It's going to drop. Okay. So if we have a snowball Earth, oxygen levels in the ocean are going to drop. What then is going to happen to the amount of dissolved iron in the ocean? If the oxygen's gone away, what happens? We can dissolve iron in the ocean again. At the end of the snowball Earth period, what's going to happen to oxygen levels in the ocean? They're going to go back up, which means the iron is going to go back down. Okay? So the fact that we get this kind of secondary period of banded iron formation at this time when other people are arguing for the snowball Earth, fits into the same story. Global glaciation, cutting off photosynthesis in the ocean, oxygen levels drop, allows iron to dissolve in the ocean water. The snowball Earth period goes away, oxygen levels build back up, iron precipitates out, and we get banded iron formations again. So this I just want to throw out as something that we see, and we'll talk about explaining it later. What we see in these areas around the globe where we're finding these glacial deposits in areas that appear to be tropical at the time, oftentimes those glacial deposits are capped by dolostone and carbonate deposits. on top. So that's another clue. And we'll come back to that. I think at this point I just want to mention that this is a common pattern we see. We see glacial deposits capped over by these carbonate and dolostone sediments, and then then we just get normal kind of geological strata following on that. And then the last piece I want to mention is also in these areas, in these deposits, we get we oftentimes see layers of iridium, which is not a very common element here on the Earth. Iridium in the geological record is oftentimes a marker for extraterrestrial material. The most famous iridium deposits mark the boundary between the Cretaceous and the Tertiary at the end of the dinosaurs era, at the end of the Mesozoic. And does anybody know how is that layer of iridium at the end of the Mesozoic interpreted? What do we think killed off the dinosaurs? Yeah, huge impactor hitting in the Yucatan, throwing up debris, causing big climate change, stressing the ecosystems, dinosaurs, which were apparently kind of on their way out anyway. It kicked the bucket big time. So in that case, we've got an impactor coming in, bringing a lot of iridium with it. That iridium gets spread around the globe as this layer of iridium-enriched material that's laid down at the end of the Mesozoic deposits. What? Dynamic spark plugs out of it. Iridium has also been implicated in the sediments that mark the end of snowball Earth, but not because of an impact, for mechanisms we'll talk about in a minute. So, in addition to those carbonate layers, we see iridium-enriched layers also at the end of the what is thought to be the time for the snowball Earth. So, how do we put this all together? The other reason I like talking about this is to bring up some concepts of system regulation. And feedback cycles. So first I wanted to just present this carbonate-silicate cycle and talk about how it functions as a feedback cycle. we have, as we've talked about, tectonic activity is what is eventually responsible for developing the topographic relief we see around the planet. Plates crash together, mountains get built up, and what happens to those mountains then over time? They get eroded, they get weathered, they get worn down. All of this activity influences the carbon cycle, carbonate rocks, and silicate rocks in a way that functions as a climate regulation system. So here we're talking about the interface basically between geological processes and climate processes. So if we just follow the carbon part of this, we get carbon added to the atmosphere as carbon dioxide coming out from volcanoes. Okay? That carbon dioxide can get bound up with water to form carbonic acid. And that carbonic acid precipitates out with the rainwater. As the rainwater interacts with the rocks in the mountains that are being weathered, that carbonic acid can dissolve minerals out. And so, point I wanted to make here is that basically when we are weathering rocks, that process involves removing carbon dioxide from the atmosphere. The more weathering and erosion that's going on, the more that carbon dioxide from the atmosphere is combining to form carbonic acid, which is interacting with the minerals, and then that those dissolved ions and so forth eventually flow to the sea, where they can get bound up into carbonate rocks and silicate minerals, and those carbonate rocks can eventually get subducted through plate tectonics. What's going to happen to the carbonate rocks as they go down into the mantle? They're going to metamorphosize, but then they're going to melt. They're going to release their carbon dioxide. And how does that carbon dioxide get back up into the atmosphere? Magma coming back up, volcanic activity. So, in your ecology classes, you talk about the carbon cycle in a more short time frame where you've got carbon dioxide in the atmosphere being taken up by plants, being eaten by animals, and then being recycled back to the atmosphere. So there's a lot of that going on back and forth here. But on a geological scale, we have a much longer time frame cycle of carbon where the weathering of rocks moves carbon and silicates and so forth into the ocean, gets incorporated into sediments. Those sediments get subducted. They get cooked by going down to the earth, which is going to be releasing carbon dioxide back again, and that's going to go back up in the atmosphere. So rather than these short ecosystem cycles of carbon that are on the order of days and weeks and years, we have a carbon cycle that's involved in plate tectonics and geology that is hundreds of thousands and millions of years in terms of its cycles. This works, however, to act somewhat as a thermostat for the planet. If the temperature rises, what's going to happen to the amount of weathering that takes place? Is weathering of mountains going to increase or decrease as temperature rises? It's going to increase. A rise in global temperature, there's going to be more precipitation, there's going to be more cycling of the carbon, there's going to be more rainfall, the chemical reactions involved in weathering are going to increase with the warmer temperatures. As weathering increases, that is going to draw more carbon dioxide out of the atmosphere, ship it to the sea, bury it in deep ocean sediments. As the amount of carbon dioxide in the atmosphere goes down, what's going to happen to the global temperature? We know this based on what we're talking about climate change today. Decreasing carbon dioxide in the atmosphere is going to do what to global temperature? Lower it. So an increase in temperature leads to an increase in weathering, which is going to suck carbon dioxide out of the atmosphere, which is going to act to reduce global temperatures. That's a negative feedback process, and negative feedback processes basically lead to essentially stable regulation of systems. On the other hand, if temperature goes down, what's going to happen to weathering? Weathering is going to go down. There's going to be less weathering to remove carbon dioxide from the atmosphere. In the meantime, volcanoes aren't stopping. Volcanoes are continuing to put carbon dioxide in the atmosphere, but if the temperature drops, weathering goes down, you're sucking less carbon dioxide out of the atmosphere. The volcanoes are putting carbon dioxide into the atmosphere. Eventually, carbon dioxide levels are going to go up. The temperature is going to go back up. And so, if temperature gets above a certain point, weathering is going to reduce the greenhouse effect, bring temperature down. If temperature goes down below too far, then buildup of the greenhouse effect is going to bring temperatures back up.
What about with all the CO2 coming down the volcanoes? Would that cause a thermal inversion and lead to a little bit more weathering?
Possibly, but things like inversions really are acting on a fairly local or regional scale, and these kinds of cycles, we're really talking about global effects that are, as I said, over hundreds of thousands or millions of years time scale. So you might think that, if we're dumping carbon dioxide in the atmosphere now, temperatures are going to go up. What's going to happen to weathering? In our greenhouse world that we're setting up, that should stimulate more weathering. That weathering should pull carbon dioxide out of the atmosphere. More carbon dioxide in the atmosphere, the ocean should eventually suck that up, and those sediments would eventually get buried deep. Why can we not rely on these geological processes to fix our climate change in response to all the carbon dioxide we're pumping up in the atmosphere? We're moving faster than the geological. In 100,000 years, all the carbon that we're putting up in terms of industrial revolution and use of fossil fuels will eventually be scrubbed out of the atmosphere, but that's going to be over the course of 100,000 years. And in terms of our day-to-day policies,
We probably won't be around.
right, yeah. So, the main points here is we have probably had a fairly stable, our climate in the past has clearly increased. We've had periods of much elevated temperatures, even above what we're pumping, even above what we're forcing today. We've clearly had ice ages in the past, so there has been some variation. But probably the Earth has been less variable in temperature than you might expect just on other forcing factors, because we have this negative feedback system that tends to, at least over long periods of time, buffer the temperature and keep the temperature in a particular range. So why then do we first of all have ice ages at all? And how then could we also have global ice ages? A whole snowball Earth thing where we've got ice down to the tropics. The flip side of negative feedback is positive feedback. And positive feedback in particular has probably been involved in driving these episodes of snowball Earth conditions, assuming that we've got good evidence for that. We know that there are orbital, well actually this is in the climate, in the glacier talk that I didn't do yet. So we have Milankovitch cycles of climate. The Earth is not going around the sun in a perfect circle. The shape and parameters of that orbit do vary over time. The tilt of the Earth varies a little bit over time. The precession of the Earth, where that North Pole is pointed, all of these things vary over time at different cycles. This particular figure doesn't give the cycles. All of these three processes have their own different cycle times. I think this one is on the order of 100,000 years, and then there are others that are on the order of like 30 and 40,000 years. So all of these influence how much solar radiation is coming in and where it's distributed on the planet. And I'll make sure we get those other slides that talk about this a little bit more, about how these forcing functions have been involved in the development of the normal kinds of ice ages. We're currently in an interglacial period. The Pleistocene glaciation basically lasted from a couple million years ago to about 15,000 years ago. We were in a period where the orbital parameters of the Earth basically were pushing that system toward colder conditions. We're now in a bit of an interglacial period. The orbital forcing functions have changed a little bit. So this kind of stuff can lead to glacial periods and interglacial periods. The kind of normal ice ages that we are thinking of with the glaciers coming down 50,000 years ago into New York and Wisconsin and so forth. But this by itself doesn't produce the kind of global glaciation that we're talking about with snowball Earth. It has to be something more that perturbs that climate system even further to drive it to a point where we've got glaciers down in the tropics. There's a couple of things that were probably involved in the two snowball Earth episodes, at least a couple of things. One is this positive feedback effect of the influence of ice pack on albedo. And ironically, we're more likely to get a snowball Earth situation developing if all of the continents are down in the tropics. Which they were back when they were coming together to form the supercontinent of Rodinia. So let's think about this. I didn't throw in a picture of the global heat budget for the Earth because you probably have all seen that kind of a figure before. What is the primary driver for the heat budget of the Earth? Where's our primary heat come from? Sunlight coming in is so many watts per square meter of energy coming in from the sun. Some of that gets reflected off by clouds into space. Other parts of that sunlight is absorbed by the Earth's surface, warms up the Earth's surface. That warm surface re-radiates heat back out to the atmosphere. You've got all of the climate mechanisms, development of weather systems and so forth, distributing that heat around the Earth. And then eventually all of the heat gets radiated back onto space, and the Earth is in a relatively balanced heat budget. Got energy coming in, cycling around, radiating back out. The absorption of that sunlight by the Earth's surface is a big component of that heat budget. Which is going to absorb more heat? A dark body of water or white ice cap? Dark body of water. Okay. So let's say that we have this kind of standard cycling process going on, leading to a regular advance and decline of ice caps. As the ice caps increase, what's going to happen to the amount of energy that the Earth absorbs? More white ice caps means less sunlight absorbed by the Earth. If we're absorbing less sunlight, if the Earth is absorbing less sunlight, what impact is that going to have on global temperatures? Global temperature is going to go down, which is going to have what impact on the amount of ice cap? Okay. So we have a situation where we've got more ice, leads to less sunlight, which leads to lower temperature, which leads to more ice, which leads to less absorption of sunlight, which leads to lower temperatures, which leads to more ice. This is not a negative feedback system. This is a positive feedback system. So positive feedback systems are inherently unstable. You get significant enough perturbation of the system, that system is not going to return to normal. It's not going to return to equilibrium. It's going to get further and further away. And so we've got these kind of normal climate cycles. If you couple that with a situation where the tropical land of the continental land masses are all in the tropics, that is going to have a couple of impacts. Again, which is going to absorb more sunlight? Relatively dark water or relatively light continental mass? Oceans actually are better absorbing sunlight than continents. So if you've got all of your continents down here in the tropics, you've got less tropical ocean. Less tropical ocean means less ability for the Earth to absorb sunlight. What do we know about rainfall in the tropics compared to rainfall in other latitudes? A whole lot of it. Okay? So if you have all of your continents down in the tropics, they're going to be being pelted by a lot of rainfall. What's going to happen to weathering rates? Weathering rates are going to be elevated, which is going to do what to carbon dioxide in the atmosphere? Suck it out. Okay? Because the weathering of the rocks, as these continents are down in the tropics, is going to require the reaction with carbon dioxide, carbonic acid. So, having all of your continents down here in a supercontinent in the tropics is going to reduce absorption of sunlight by the tropical oceans. It's going to increase weathering, which is going to pull carbon dioxide out of the atmosphere. All of that is going to exacerbate the lowering temperatures, which allow the ice caps to grow bigger and bigger. The more the ice caps grow, the more sunlight is reflected out into space and not absorbed. It's going to just continue to exacerbate this. So with the right conditions on top of these normal kind of climate cycles driven by normal orbital changes, you can get a situation where more ice leads to less sunlight absorbed, leads to lower temperatures, leads to more ice. And this process, nothing's going to stop this process until the glaciers have just covered the whole planet. So that's pretty bleak. Right? It's like, what was that cheesy climate movie, The Day After? Day After Tomorrow? Where we have all of a sudden, over the span of a couple of weeks, glaciers enveloping New York City. Yeah. But, I mean, given the way these positive feedback mechanisms work, given the influence of elevated weathering rates and decreased absorption rates because of the placement of the continents, given the impact that will have just on the climate systems in general, you can push the Earth into a situation where it enters a positive feedback system. Once it's in that positive feedback system, there's no stopping it basically. More ice, less sunlight, lower temperatures, more ice, less sunlight, lower temperatures, until you've got just ice covering the whole planet. When people realized that there was this positive feedback possibility, then the question became, well, how would we ever get out of a snowball Earth situation? Right? If the whole Earth is covered by ice, there's not going to be a lot of absorption of sunlight. How are you going to flip the switch back to get out of this? Any ideas? What are we doing now to warm up the planet? Volcanic activity. Volcanic activity is not going to stop just because the Earth is covered by a sheet of ice. The volcanoes are going to continue to pump out carbon dioxide, because that's what they do. They're not going to become more active, but they're also not going to become less active. Volcanoes are volcanoes. They erupt at a certain frequency, and as they erupt, they put carbon dioxide in the atmosphere. If the whole globe is covered with ice, is there any way for that carbon dioxide to get out of the atmosphere? No. There's not going to be any rainfall bringing the ice, the carbon dioxide out of the atmosphere. There's not going to be any exposed continental shelf material to weather. And so if the volcanoes are pumping carbon dioxide in the atmosphere and there's no way for the carbon dioxide to get out of the atmosphere, what's going to happen to the carbon dioxide level in the atmosphere over time? It's going to go up and up and up. Much more than we're doing right now. So at some point, you're just going to get so much carbon dioxide in the atmosphere from these volcanoes that even though the land surface is reflecting sunlight away because of the ice, it's covered with ice and that's reflecting sunlight away, you still have enough carbon dioxide in the atmosphere to absorb enough heat that it's eventually going to lead to a massive greenhouse effect. And that will overcome the albedo effect of the ice, and you'll start melting the ice. Once you start melting the ice, what's going to happen to absorption of sunlight? If you start getting some open water in the tropics, not covered by ice anymore, what's going to happen to the absorption of sunlight by the planet? It's going to increase, which is going to augment this greenhouse effect even more, which is going to lead to more melting of the ice, which is going to lead to more absorption, which is going to lead to more increases in temperature, it's going to melt more ice, and so basically you come out of the snowball Earth by going into the opposite positive feedback mechanism. You have enough carbon dioxide in the atmosphere forcing absorption of heat radiated back out from the Earth, that is forcing an initial melting of the ice, which leads to more absorption of sunlight, increase in temperature, more melting, more absorption, more temperature, more melting, till the whole thing, reverses back to a non-glacial period. Okay, so this is just kind of summarizing this. We can go into a snowball Earth effect if there is, the right conditions to get us into a positive feedback refrigeration kind of mode. And when that happens, increased ice is going to lead to decreased absorption, which is going to, just push us into the greenhouse. We have basically volcanoes pumping out carbon dioxide, leading to enough global warming that we get positive feedback going out the other way. So if this scenario actually does play out, then why do we at times get these low latitude glacial deposits? Because something has kicked us into snowball Earth positive feedback mechanisms, and the glaciers just blanket the whole globe. We talked about how covering the ocean can lead to a decrease in photosynthesis and those changes in carbon-13, and how the lack of oxygen in the ocean can allow iron to dissolve during the snowball Earth time period, and then when it breaks, when we have the runaway greenhouse effect, there's going to be lots of oxygen in the atmosphere. That oxygen is going to dissolve back into the ocean. It's going to cause the iron to precipitate. Why would we see extensive carbonate deposits on top of the glacial deposits that we see from a snowball Earth impact? Why? Okay, snowball Earth is over. During snowball Earth, we see the glacial deposits. That's followed by carbonates. Why? The volcanoes have put so much carbon dioxide in the atmosphere that that's followed up with, once the ice sheets melt, that carbon dioxide can get taken out of the atmosphere again by the ocean. We're going to get a lot of carbon dioxide in the oceans. That's going to produce various kinds of limestones and dollostones and other kinds of carbonate sediments. So if we're at like 13% carbon dioxide at the end of a snowball, to break a snowball Earth effect, that carbon dioxide itself is going to get scrubbed out of the atmosphere by being taken up by the ocean and deposited as these layers of carbonate rock. Now, in terms of the space dust, if you have the planet shrouded in glaciers, is that going to stop meteorite dust and so forth from falling on the planet? No. It's just going to kind of rain down on the ice. Boom, 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 boom. Then when the ice melts, what's going to happen to all that space dust that accumulated in the ice? It's going to settle into the water, forming a relatively concentrated layer. Okay? So this idea of a snowball Earth works to tie all of these different geological observations together into a story. Now there are arguments against snowball Earth. It may be that there were, even at the height of glaciation, there were open water areas in the tropics. So some people instead argue for, slush ball Earth model. And there are a couple of alternate explanations as well. So I've presented a fairly simplistic story, but the main points about the Earth getting perturbed into a positive feedback regime, where more ice leads to more ice, essentially, through less absorption and lower temperatures. That presumably has happened at least several times in the Proterozoic. And whether that resulted in a complete casing of the Earth by ice, or whether it was just mostly down to the tropics, but there was still some band of open water. Those are the fine points that geologists are arguing about. But the general picture is probably a reasonable explanation of what's happened these couple of times in the past.
So, starting this snowball cycle would lower the Earth's temperature. Why not temporarily increase Earth's albedo with just white things, what kickstarts that cycle, and you can figure out what had to put in the carbon emission?
Yeah, there are lots of ways we can geoengineer the planet. We're geoengineering the planet right now by pumping not only carbon dioxide, but we're also elevating methane levels and some other greenhouse gases. So that's pushing the climate system toward higher temperatures. We could, it's not like we're going to paint all of northern Canada white, but we could put aerosols up into the atmosphere that would reflect light back out, that would increase the albedo of the planet.
What about ecologically dead areas, like Death Valley, mostly Gobi Desert?
We could paint roofs white in the city, which some people do. And that's going to have more of a local heat budget impact than climate one. But so currently we're forcing the climate system in one direction. There's nothing that would prevent it necessarily from getting into another kind of snowball Earth situation, depending on if we had continental drift accumulate all of the continents in the tropics again, we potentially could be driven back into carbon sequestration is probably going to be a more effective geoengineering solution than massive activities to adjust the albedo of the planet. But people have been thinking about all sorts of different things to try.